Alright, suppose you have 4 boxes of the cracked corn cereal. Remember that each box has an equal probability of containing any one of the 7 collector cards. This is part 3, where they're asking for 2 identical and 2 different cards. Okay, so you have to bear with me here, because this is going to be a lot longer than normal. Let's delete that, let's delete that. Okay, so there's 3 different ways of trying this. So the first one, similar to what we did in the previous 2 questions, I'm going to lay out the 4 different cards here. And I'm going to have to spell this out a little bit more, so that's why I make myself some more space here. For that first one, we have 7 choices. So we have A, B, C, D, E, F, and G. Okay? So that's right here. That's a 7 out of 7 chance of getting one of these things, right? Getting one of those cards. And then, for this card, let's count the number of ways to get the same identical card, because that's what they want, 2 identical cards. So A and A, B and B, C and C, D and D, dot, 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 dot. Now this is also going to be G and G, right? So really, there's still going to be 7 ways. Sorry, rather 1 way. There's only 1 card we can choose to have in this slot here. So it's going to be 1 out of 7 choices. It's got to be 1 out of these things here. Now, the next ones have to be different. So if it was A and A, we have a choice between B, we have C, and then we have all the way down to G. We cannot choose A, so we no longer have 7 choices. We now have 6 choices. So 6 out of 7 chance of getting a different card here. And then the last one's got to be a different card from this one and this one. So here, in our final part of our tree diagram, this has got to start with C, and it goes down to G. And here, this starts with B and goes down to dot, 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 G. Okay? And so we have 1 less choice now. So we have C to G, C to G, that's 5 out of 7 choices. Okay, so at this point, we've done this situation where we pulled an A first, and we had to pull the A second, and B third, and then there's a C there. So I'm going to lay it out over here where we have 1, 2, 3, 4. We have A, and then B and C. I'm going to try to keep this as a little bit of a package, because we're taking into account right here the situation where B comes before C. We've already taken into account C coming before B in another situation. So I'm going to count the number of possibilities we can rearrange A, B, and C. Because in this part of the tree diagram, this is the only time where we can have 2 A's. Alright, so how many different ways can we rearrange A, and B, C, such that B and C is always before C? So an easier way of rearranging this is just focusing on 2 of them. So where would you put the A's? So you can put the A's there, or here, there, or there, and there, and there, and there, and there. 1, 2, 3. Oh, there's going to be 1 more. Oh, the last one's, I skipped one. This one. Okay, and because B and C have to be in the same order, because we've already taken into account and counted for CB, really there is going to be 1, 2, 3, 4, 5, 6. So do you see how really what I did here was I had 4 slots and I chose 2 of them? So really, how many different ways are there to rearrange this? There are 4 choose 2 ways of rearranging that. So how many different ways are there to rearrange each of these? Like this one? How many different ways are there to arrange this one? Right? Each of them we can rearrange in 4 choose 2 ways. Okay. Another way of thinking about it is you can rearrange it. So we have 4 slots here. How many different ways can we rearrange it, right? So there's 4 slots, there's 4 factorial. And if they're not all identical, right? 2 of them are the same. So that's, we had to divide out the 2 factorial. And because we don't want to count the BC's and the CB's separately, which is in that 4 factorial, we have to divide out the number of ways you can move B and C around, so you divide by 2 as well, or 2 factorial, which is the same. Okay, so you can think about it as 4 choosing 2, you're choosing where to put your 2 A's, or you can think about it as 4 separate cards to rearrange, and the fact that 2 of them are identical and these 2 are apparently identical, or you can't switch them around, that's why you can divide by 2 factorial. So you can, it's this, I don't even know what that is. So that's going to be 7 over 7 times 1 over 7 times 6 over 7 times 5 over 7, and there's 2 choices, times 4 choose 2, or times 4 factorial over 2 factorial, which is 2 factorial. Now, they have the same algebraic meaning, but visually what is happening between these 2 things are totally 2 different things, 2 different ways of counting, 2 different ways of thinking about it. And this is very important for like computer science especially. The flexibility of numbers and the fluency of numbers is what you need to do, which is why we're going to be asking you to solve things in 2 different ways, like this, and think of things in 2 different ways. Okay, this is the way a computer cannot do. Computers don't think like this, they only think in one way, they just calculate, right? This is art here. It's beautiful to be able to see numbers in 2 different ways. Okay, so let's calculate this. So that's going to be on the bottom, it's going to be 7 to the power of 4. And this will be this to the bottom. This will be 7 times 6 times 5, 7 times 6 times 5 times 6, which would be 1260. So 1260 divided by 7 to the power of 4 is 180 over 343. So that's method number 1. This is method number 2-ish. So sorry, this is method 1, this is method 2. They both end up being the same. Let's talk about method number 3 here. If I could zoom out here. All right, method number 3. So we have 7 for that first card here. We have 7 choose 1 different ways of doing this, because we have 7 cards to choose from and we got to choose one of them. And this one right here is we're just counting the number of ways to get the 2 identical and 2 different cards. So if this is going to be identical, we're going to have 1 choose 1 here. So that's going to be the identical card. And right here, this is going to be these 2. We have 6 cards to choose from, and we got to choose 2 of them. Okay. So now, again, we've calculated this in a certain order. What we need to do is we need to multiply by 4 factorial, and because we can rearrange them in 4 different ways, and then because 2 of them are identical, we divide by 2 factorial. And so, try that out. 7 times 1 choose 1, I think is 1. 6 choose 2 times 4 factorial divided by 2. It's going to be 1260. Oh. Okay, so this is the number of ways, and that's the same thing as that. So again, to calculate the probability, we have to divide 1260, probability of this event. I didn't even do a let statement. Probability of event A, let's call it probability of event C, equals 1260 over 7 to the power of 4, which will be 180 over 343. All right. There's a fourth way of doing this. Okay. This one we have 1, 2, 3, 4. And again, what we have here, we have to choose two identical spots for the cards to be. So we have 4 spots to choose from, and we got to choose 2 of them for the identical spots. So where are the identical spots going to be? There's 4 choose 2 ways of putting the identical things. It's similar to this. Okay. Now, what we can do now is that we have 7 cards to choose from, right? And we have to choose, there's going to be 3 different cards, right? One set, one pair, and then there's 2 more. So 1 set of cards, and then 2 more here. So we're going to have 7 cards, and we got to choose 3 of them, right? And so now that we have that, we have to rearrange those 3 cards that we have in order. So we have to multiply by 3 factorial here. And then, so this is the number of ways that we have, number of ways of getting 2 identical and 2 different cards. And again, we divide by 7 to the power of 4. And we do 4 choose 2. 4 choose 2 times 7 choose 3 times 6, again, is 1260 over 7 to the power of 4. And again, it's the same answer as that. Okay. So you have 1, 2, 3, 4 different ways of doing this. And it's very cool to think of it in either in probability ways or the combination ways, and you can think of combinations in different ways here, okay, to get the same answer. All right, let's go on to the next video for part 4.